So, good afternoon. Last presentation today, before dinner. It's about satellite orbit determination with GENSO, the Global Educational Network for Satellite Operations. I was actually hoping that there already was a GENSO presentation, but it was not the case. GENSO, in two sentences, it's a global network of amateur radio and university stations trying to monitor CubeSats or other educational spacecraft, and they want to reach 24/7 communication all around the globe. That's the ideal situation. That's not really the case, but that's the main idea about it. And the idea was, when you have GENSO, all ground stations spread around the world, can we do orbit determination ourselves? Can we provide TLEs ourselves? Why am I going to do this? I was looking for a Master of Science project, and I contacted Neil Melville. Hey, do you have some nice projects? And there actually were 10 projects, so I selected this one out of it. And it's a nice combination of my part-time study at the Open University in the Netherlands and the radio hobby. And I'm also a computer scientist or a software engineer, so that's a good combination. The official title is Orbit Determination with GENSO, but actually it's also a little bit like two alternative approaches to orbit determination. I picked two out, which I worked out further, and there's, I think, a lot more opportunities to do, but I only picked two. And why do we want to do orbit determination? Because NORAD might stop providing TLEs. I don't know. The second is the most important one, I think. It's scientifically interesting to do so. You need a project, and it's really nice to see if you can do it yourself instead of getting the TLEs from NORAD. And it's also going to be a little helpful in the launch and early operations, which was not exactly the topic of my research, but there's a lot of fiddling around with the TLEs after launch, so maybe this can help a little bit in that. The whole project is based on the GENSO ground station network, but I think it will work with any collection of amateur radio-like ground stations or satellites. So when you have GENSO 2 or whatever, it should also work. But I think GENSO is the first one to be operational. So the question is, GENSO able to create TLEs by itself? High-level question. That was the problem statement of my research project. And some bad thing about it, because GENSO is not designed for orbit determination. It uses prediction based on a TLE, and it does not measure anything on the satellite. It just predicts where the satellite is, just tracks it, and that's all. On the other side, GENSO had a lot of resources, ground stations, all connected together, so you can collect many low accuracy observations and try to do the orbit determination. So there's a bad side and a positive side. Another thing which I had to handle, there was no operational GENSO available yet during my project, so I'll come to that later, how I solved that problem. So GENSO and orbit determination in general, when you're using GENSO or your own radio station, you cannot do any distance measurements from you to the satellite. That's what you need for orbit determination, but in general it's not possible. Also no direct angle measurements, elevation and azimuth. You can guess a little bit around, but not so precise. And actually there's no direct frequency measurement possible. You can tune your receiver, but it's no active searching or whatever. And also what a little bit the problem, it's relatively low profile ground stations. We all have really nice ground stations, I think, including myself, but it's uncalibrated, and with respect to orbit determination it's quite low profile. In respect to orbit determination, not in respect to receiving satellites when you know the TLE. So GENSO was not operational yet, so I started to make a simulation model, not with SDK unfortunately, or I don't know. And a simulation model was needed to test the orbit determination methods, developing and testing in the end to see if it was working. And I created some ground stations, antennas, receivers, satellites, and I simulated the reception. And actually the simulation model was a combination of theory and also a lot of practical advice from the AMSAT community. So thank you, a lot of people sitting here providing me a lot of things. And one reason to do it to program myself in Java was because there was already an SGP4 orbit prediction algorithm which they've programmed or translated, which I used, so thank you, it saves me a lot of time. And because GENSO uses that SGP4, I think my simulation system is close to to GENSO itself. What I did was one SGP4 instance running in my simulation model, simulating the real satellites, and the other part of the program was trying to find that orbit, that TLE of that satellite. So they were running in the same program, but they didn't know about each other, so that's still fair, I think. And what was important for the simulation model was configurable, so different experiments can be performed, and actually halfway there were so many parameters and combinations possible, you can spend years on testing all combinations, so I had to select only a few to look at the basics of orbit determination. And thanks to the Delphi C3 team, I got a list of all stations which provided telemetry information, downlink information for the Delphi C3 network, and that configuration I used in my simulation model. So here you see 90 stations. There's a lot of in Europe, of course, and North America, some in Australia, and actually there were 220, and split it up in 3 different parts simulation model, so you can compare a little bit. But it's a typical ground station distribution, I think. We also saw it with the Compass 1 mission, at the same kind of distribution. So no ground stations in Africa, for example, or some in Russia, but not too much. Block diagram of the simulation model. On the left you see a small database with all the ground stations in there. It will be loaded into the Java application, which simulates your satellite. It also simulates reception events or reception by ground stations, which is stored in another database. That's running on one part. The other part is the orbit determination process reads back all the reception data and tries to reconstruct the orbit. And on the left you can do some simulation settings. You can set the output power of a satellite, you can load different TLEs, and that's not important on the right. So that was the simulation system I had to build before I can even start. And then there was only time left to test 2 different strategies or methods for orbit determination. And I called them the static mode orbit determination and the tracking mode orbit determination. The static mode is about when you have no information at all about the satellite, only the frequency which it transmits on. And the static mode is based on try to reconstruct the ground track of the satellite and extract the TLE out of that. And the tracking mode is actually when you have a TLE where you can receive some satellite data, and it's more based on a search algorithm, a little bit artificial intelligence, kind of. And to make it a little bit simpler to start, I assumed LEO satellites, which are focused on, have a circular orbit, which is almost true. So you get rid of 2 parameters, you only have 4 left. And for LEO orbits it's only a small error. Actually with amateur radio stations I think you won't even see the difference. And the orbit determination principle is only based on reception of satellite signal. So there's no round trip measurement or whatever, just take it as general as possible. At least the satellite will transmit something, I think. So that's the most basic thing you can expect. Other techniques were considered and passed by, like automatic frequency control or discriminator readings or software-defined radios, but there was no time to do it all. But they all passed by, and maybe another student or whatever can do that, or maybe I will do it later. And also focused on basic equipment, unmodified ICOM or Kenwood radios, and just standard antennas, no phased arrays or whatever. I think it will work fine, but that's not GENSO. GENSO is just basic stuff. And there will be a central entity in the network who is organizing all the orbit determination, of course, doing the distribution of TLEs or whatever. So one of the two methods, it's static mode orbit determination. Only the frequency of the satellite is known, no other orbit information, only that's a LEO satellite. What we do, we actually, with all the 90 stations, we wait for a satellite to pass over, put the antennas fixed up, and wait until we receive something. That will be mostly when it's straight up, at the time of closest approach, when also the Doppler shift is 0, because you're also tuning on the transmission frequency. And what you actually do is you measure the position and time when the satellite is straight over, so that's actually 1 point of the ground station of the satellite. And with that principle, the ground track will be reconstructed. What you see in one pass, antenna straight up, no Doppler shift, you get a set of observations which you will average out. You take the average one, the middle one, which is in the middle of the time, and it will also be in the middle of the pass. And for every observation, every ground station, you will do that, and all the errors will average out on average. It's not precisely, but when you have 90 stations of satellites, it will do the job, as you see later. And the main principle behind it is when you reconstruct the ground track, the Earth will rotate underneath it, but when you correct for that, then you have a really stationary ground track. So you have to correct for the rotation of the Earth, as one, and also correct for the nodal regression, because the Earth is not exactly round. The orbit itself will turn a little bit, and the rate of the turning is depending on the inclination and the speed of the satellite, which you don't know in advance, so there's a little bit of trying and iteration to get it right. So when you plot all the observations which you did in the network on a map, on a world map, without a correction, you get like this, which actually the ground station distribution is Europe and the United States, some New Zealand and Australia. And we do the Messier correction. You see this, you correct for the rotation of the Earth, and then your orbit will appear. And you actually see the inclination. This is 55-degree inclination. It's here. It's also this line is the 55 inclination. Orbital period of your satellite, of your TLE. You have a lot of observations, and you look for one observation and the other one which is closest by after the correction, and then you get a multiple times of your orbital period. With some mathematical equations you can lower it down to one orbit. Inclination is also based on the rotation, and we use the least squares fit to look at all the points. And when you rotate the Earth, you suddenly see it's appearing on one line when you're right, and with some mathematics you find the right line and the inclination. When you have the inclination, you start do the nodal regression again in 5 iterations. In the end, it's quite right. The right decision of sending node and mean anomaly, I will skip it because it won't fit in the half-an-hour presentation. So, is this working? Yes, with the simulation model. What you see is 2 configurations, A and B. That's different ground station configuration. One LEO satellite. And horizontally it's the orbit determination time, which is 1 day, 2 days, 3 days. And on the vertical axis you see the reception quality, what maximum can be received. And with this method, after 2 or 3 days, you get 100% of reception with your GENSO network. And it's also depending a little bit on the ground station configuration. A is a little bit better than B, because A is more equally spread. and B is more concentrated in Europe and US and less in Australia, so it takes longer to get there. But eventually in the end you will reach 100%. But still with the simulation model, so we have to check if that's really true. And then testing two different satellites, SwissCube and PolySat CP6. SwissCube is 97 degrees inclination, PolySat is 40 or so. So it's quite equal, quite the same for this one. We did a lot of experiments, but putting in all in 2 lines. After 2 days we get TLEs which can be used to track the satellite with a system like GENSO. That's the overall conclusion of the method, of the static mode orbit determination. The other one is the tracking mode. You know something about satellite, you know an initial TLE. What we're going to do is actually track the satellite. That's what's called tracking mode. And what we do is we take one parameter of the TLE, just tweak it a little bit, put it a little bit higher or lower, and just test that TLE, how it's behaving. Is it better or is it worse? And we do it with all 4 parameters. You have 90 stations or less or more, but you can assign different TLEs to different stations and then get the reception data back and say, hey, this was better, this was worse, and so search for your best TLE. And actually you need some smart quality management, because you say what is better and what is worse. When you don't know the real orbit, how do you define best or worse? So I make comparison between the predicted observations and real observations. But here you get a loop of you have a TLE. You predict the AOS, LOS and the time of close approach, and you also do the real observations and you compare it, and when it's matching it's 100%, when it's half matching it's 50%. It's a bit more complicated, but it's the main principle. Just compare the predictions with your observations. You get a grade for that. This is an example for the mean motion. This is the correct mean motion. When you have a TLE with a lower one, the quality goes down, and a higher one, the quality also goes down. And we did also some filtering, because it was quite noisy signal, so you did some digital filtering in there. And see really the peak on the correct one, and when the mean motion is off, you see the quality going down. So the results of the tracking mode, it's not 2 days, it's going to be a little bit longer. It's not so effective. It's going up to 100%, but it never reaches the 100%, and it's taking 4 or 5 days or so. 2 configurations again, A and B, like the static mode results. And then we compare the SwissCube with the PolySat. The SwissCube is doing quite fine. The PolySat is not, because it's a low inclination and we don't have so many ground stations at low inclinations. So this method is not working so fine. Maybe we have to reschedule the TLEs to the correct ground stations. I just reschedule or schedule them randomly, so maybe that needs some improvement. So after 5 to 7 days, the reception quality, so 90 or to 100% of all the packets you expect are actually received with this method, except from some low inclination orbits, which have to be improved. So what did I put down in my thesis in the end? We had a proof of concept for orbit determination with GENSO. Actually, we investigated two methods. And it was a method for the entire lifetime of the satellite. Most of the time you know the TLE, but when it's not the case you can use the static mode. And the idea was to further get on with the tracking mode, but we have to see if that's the best solution. We also see that the static mode is better than the tracking mode. But what you see with the tracking mode, you're actually receiving data, so maybe in the end it's not so performing so well, but you receive more data, and that's actually what you want to do with GENSO, receiving data. So that's a trade-off you have to make. And I think the first thing we have to do when GENSO gets operational is get the data in and run the algorithms with the real data and do some real-world adaptations in the algorithms, I think, because it's not working so perfect as my simulation model, I think. So I did a lot of work, but I will also want to acknowledge ESA for organizing GENSO, the people from GENSO, which had a lot of nice discussions with. A lot of radio amateurs helped me, so thank you. My employer supporting me in time and money to do my study, and my family, of course, supporting me. So that was orbit determination in a nutshell. I can talk about 2 hours more about it, but I want to leave it in 20 minutes, half an hour. Are there any questions?
Any questions?
Hey, Neil.
He's always got.
Hi. I'm particularly impressed with how quickly the static determination finds it. That's quite surprising. It's a nice result. Intuitively, you would think that the tracking version should do better, because of course you're starting with better than no knowledge and trying to improve it.
Mm-hmm.
So I'm curious as to why it didn't. In the tracking mode, were you still just taking the middle value of the receptions, or was it taking into account that each station did know where its antennas were pointing when it got each packet?
Yeah, you know that, but what I do for the quality is compare the acquisition of signal, loss of signal, and the total pass time, and another thing together to get. I fiddled around a little bit with that, and I found the best combination for it. But actually, you can use the direction of the antenna, but it's the predicted direction. It's not the real direction, so that's a little bit hard to say if the satellite was really there. It must be somewhere there, but.
Yeah. But you see what I mean, that intuitively you'd expect the tracking to be better. So I was wondering if you had any ideas of how you would change or upgrade the tracking version in the future if you had more time.
Yeah, I think it can be improved, because now I just assign TLEs randomly. When you do it more smarter to the correct station, it will work better, I think.
Okay.
But just a lack of time.
Very good.
Any more questions? Yeah. Yes, Ken.
We have a question on the internet from Isis Gerard. The question is, thanks for your excellent presentation, but is the performance of the orbit determination system dependent on the downlink of the satellite? And also, can you say something about the frequency, modulation type and transmission interval?
Yeah, so the first question was, is the orbit determination process depending on the downlink of the satellite? Yes, it is. I did these simulations with one packet every 10 seconds continuously, so also in Eclipse. Yes, it's really depending. When there's less transmissions, it will perform less. When it's not transmitting, when it's on the sunlight, it's taking longer. So yes, it is. And the second question was, sorry,
Yes, he was asking about the frequency modulation type and transmission interval.
Yeah. I took that in account, different ones. Actually, I compared the AFSK with the PSK, I think, the high speed and low speed. And on the static mode, the AFSK is working better because it's a wider filter. And on the tracking mode, the wider signals, the 9600 is performing better because it's early. When you have a wrong TLE, you will see it earlier because it's running out of the filters earlier than the smaller signal. So that's depending on the Doppler shift error, which you see earlier. So yes, I did some tests about that.
Thank you, Ivo. I think that will satisfy them.
Is that all, Ken? Any more questions from the floor? Well, if I can just break for a minute, I'd like to say bienvenidos to our viewer in Uruguay, and also welcome to the viewers in Los Angeles. And I hope you've enjoyed the presentations. I'd like finally to thank Ivo very much for his very interesting presentation on a very interesting project, and it's surprising what you can do with something that hasn't been designed for the job.